MED's software library for modeling and simulation of solar desalination systems. www.reslibrary.com.
Hi everybody, Professor Muhammad Sharaf with you. Let's talk today about concentrated solar power, especially concentrated solar ranking cycle for multi-effect distillation, parallel configuration desalination processes, and power generation. What is the main concept? Plant operating conditions, modeling by its library, and expected results from such configuration. First of all, the main concept is simple. It's how we can utilize a huge solar power by concentrated solar cycles, concentrated solar power to generate electricity by Rankine cycle, and at the same time we can desalinate some fresh water for remote areas, tourist spots, and so on. Okay, for power generation based on solar cell medium temperature collectors, it's simply are powerful enough to cover power demand around tens of megawatts based on Rankine cycle concept, steam Rankine cycle. The primary advantage of concentrated solar Rankine cycle is that it can operate up to medium range of temperatures up to around 400-500 degrees Celsius, and by the use of inexpensive heat transfer fluids such as terminal heat transfer oil or even molten salt. Okay, as you can see here, our main cycle is components are parabolic trough field operated with molten salt. Okay, this molten salt. We are going to use a storage tank with a tire pump inside. Okay, the solar radiation received by the parabolic trough collector is going to heat up the molten salt up to 500 degrees Celsius. It looks like lavas or something like this. This stream is going to be stored in the storage tank integrated with steam generator. This is a heat exchanger boiler storage tank. So it will transfer 500 degrees Celsius to the steam, to the water side, in order to transfer it to become superheated steam. And this superheated steam is going to drive on or power on the turbine units in order to deliver the electricity to the main grid. Okay. The rest of the steam or condensed steam is going to be condensed at the first effect of MED, multi-effect distillation. When such a steam driving or motive steam or driving steam is going to power on the MED thermally in order to desalinate seawater for freshwater production. I mean, MED in this concept, we are going to examine just two effects for 250 meter cube per day. Let's go and see how we can do this. Okay, this is a plant operating conditions. Solar radiation we're going to assign at 500. Just this is some input. This is table 1 for just this is input, the main input data, ambient temperature, molten salt top temperature. We are going to assign at 550. This is tank efficiencies. Pump inside the tank, it's around 75% efficiency. Top tank temperature, concentrated solar Rankine cycle temperature, we are going to assign it at 270 degrees Celsius as a dry saturated temperature. Condenser temperature for the MED is we are going to adjust at 70 degrees Celsius. This is the effectiveness of the boiler heat exchanger unit storage tank. Turbine efficiency, pumps. Number of effects for the MED side is adjusted at 2 effects. For productivity of 250, just we sure by our model we can assign a number of effects up to 12, 16, whatever. A prime blow down temperature, it's around 60. This is a feed salinity for Mediterranean because this plant is operated. Its location at Burj Al Arab in Alexandria, Egypt. This prime blow down salinity, in the condenser effectiveness, and MED pump efficiencies around 70, 75. Okay, how we can run our model in order to explore some design aspects for solar field, load on the pumps, MED, energy streams, exergetic streams, and exergy economics or thermoeconomics stream. Let's go and find out how we can run our model. Okay, opening our MATLAB, we are going to our destination folder and then let's run our model. Okay, here we are. This is our model. Should appear like this. There's some documentation. Okay, this is our plant. Perpector collector, boiler heat exchanger storage tank with entirely pump unit inside it. Turbine unit, MED, we are going to assign it. This is a pump unit for steam Rankine cycle. Okay. This cost analysis block and some performance analysis we are going to discover. And this is the inputs data for our model. Okay, that's from the beginning. Assign some inputs. Okay, this for information. Yes. Okay, for some physical properties, this is ambient temperature. It's around 25. It's okay. Solar radiation, I'm going for 500 as intermediate watt per meter square. Okay, this is outlet molten salt temperature. It's around 550. Okay, and dry saturated, I'm going for 270. Like the actual plant in located in Alexandria, it's 270. This is condenser steam. This is for MED. This is the condenser. The first effect of the MED is going to act as the condenser unit for the steam Rankine cycle. Okay, and this is a plant productivity. Sure, we can. Yes, we can control our productivity. I'm going to 250. Okay, hit apply. Okay, let's go inside. There's some inputs for perpector collector. It's operating hours. This hydraulic mass flow rate in order to discover how many loops you are going to design. It's up to the designer. Collector widths, gas envelope. This is actual data for the actual plant. Okay. For boiler heat exchanger storage tank, yes, the same. The tank diameter, chill diameter, inner tube diameter. Okay. Physical properties. Yes, this is a superheated temperature. Yes, I think this is 445. Okay. Efficiency of effectiveness of the evaporator inside the tank. condenser, heat exchanger, I'm sorry. This is tank pump efficiency. Okay. For turbine unit, we are going just to efficiency of the turbine and generator block. MED. For MED, this is seawater temperature. You can control it. Brine blow down, it's 60. This is seawater salinity, 35. This is salinity ratio, and this is blow down salinity ratio. Sure, okay. And this is pump unit. We are going to assign the efficiency. Okay, I'm trying to check everything. This is the capital cost, load factor, interest rates, okay, everything is fine. Okay, let's hit run and see what is going on. Okay, now this is MED. I'm sure we are. Yes, no, yes, design. Yes, this is design limits, shell diameter, tubes diameter, and number of factors is a matrix, from 1 to up to 2. And let's go and see now if we hit run. Okay, there's some results, as you can see here. This is distillate exergy, Rankine efficiency around 22, exergy inlet, total exergy destruction rate, total steam flow rate, it's 1.39, total steam cycle flow rate. Solar field flow rate is around 7.4 kilogram per second. This performance ratio, specific power consumption, per of solar field area, steam power, pumping power pump, turbine power, and this is hourly cost, total hourly cost. Let's go for per and see what is going on here. Yes, as you can see here, you can discover the pressure, enthalpy outlet. This is for molten salt. This solar field area, total length, Reynolds number, loop length, number of loops, number of solar field collectors. It's around 18 solar collectors. This efficiency around 70s, and this collector hourly cost and thermoeconomic exergetic stream. This from the collector to the boiler heat exchanger unit. This is the cost of the stream. Okay. For boiler heat exchanger, you can discover the total mass, total volume, storage height, flow level in the storage tank, pressure, thermal load, enthalpies, temperature, entropies. This is outlet vapor pressure around 55 bars. This is mass flow rate through the solar field, effective area, number of tubes, exergetic stream. This is exergetic stream parameter from going to the from the pump inside the tank going to the solar field. Okay, for turbine unit, yes, we are going to generate 1 megawatt. This output power 1 megawatt, almost 1 megawatt. Okay, enthalpy out. This outlet temperature. This is going for the MED. This is MED going for the MED outlet temperature, actual temperature. Entropy. This is dryness fraction. Dryness fraction. It's around almost 1. Fine. And some exergetic and energy analysis. This is MED. Yes, this is total steam flow rate. This total steam flow rate going. This is for steam cycle. This feed flow rate. This distillate profile per effect, because we are going to operate 2 effects. Brine profile, salinity profile. This pressure condensate. Entropies. This temperature profile for the blow down, vapor gain ratio for 2 effects, areas, length of the tubes inside, the H effect. Totally this is the end condenser. Okay. Feed flow rate, cooling water. This is cooling water flow rate. Total feed flow rate. This is feed burn temperature. Okay. Distillate temperature from the in the condenser. Area, total area. So 1.109. Okay. Tube length, number of tubes, and so on. Okay. And sure, we have distillate pump power, 17 kilowatt. Okay. Distillate pump power, feed power, 17. And this is prime breakdown. Okay. This is thermoeconomic. It's around 0.6 dollar per gigajoule. This is thermoeconomic unit product cost. This is very important. This is the conclusion of the price related to the exergetic streams. So this is a very important parameter, and so on. Let's go for this is the pump. This is considered solar Rankine cycle pump. We consume around 10 kilowatts, and some economics. This is MED hourly costs. This total cost. Yes, this is a unit product. We are going to sell our total water price. We are going to sell our product by almost $3 per meter cube, because we are going to desalinate just 250 and chemical cost and so on. The sum performance, specific bulk consumption almost 4.6. This is our gain ratio, total irreversibility of the plant, Rankine efficiency, and exergetic efficiency. Okay. Let's go for, we can choose, sure, we can control some inputs, we can change, we can go dynamically. I mean, we can go dynamically and change some parameters. I mean, let's go for infinity time. Okay, these are our inputs. Let's try to change some inputs. Productivity, plant productivity. Let's go for the plant productivity. I'm going for 1000, for example. Let's see the effect on, for example, turbine unit. Let's see here. Let's see if we change it. Let's hit run. Let's change. Yes, increasing the plant productivity would increase the power, because we are increasing the mass flow rate through the turbine unit at the same temperature and the same operating condition of I mean the constraints of the unit, going for 1000, 2000 meter cube per day up to 5000. Let's see, 5000. Let's show increasing the irreversibility, everything will increase just for two effects. I'm going for two effects. Okay. This is 5000 meter cube per day. Okay. Okay. Let's stop and see our results. Yes, for example, this is almost, let's see, performance ratio will not change, because yes, this is total hourly cost is increased, and solar field area sure increasing, because we increased the mass flow rate. And steam power, this is a pump power, this is pumping power. Okay, the same effect. This is solar field mass flow rate, sure. And the perpendicular of area, yes. Let's go for gain ratio, total exergy, yes, total pumping power, a little bit increasing. This turbine unit power, this is the power of the turbine unit. I mean, the same effect. I'm sure you can change temperature constraints, you can change number of effects, you can change many parameters in order to discover the effect of such a change. Let's go for 250. I'm returning to the original case. Let's go for this. It's 250, almost 1 megawatt power, and this is steam temperature from the turbine, and this is condensed steam. Okay. Okay, it is clear from our model that we can discover the following. These inputs, some inputs, as you can see before. Per vector of eddy temperature, it's around. You can control this temperature by the effectiveness of the voltage exchanger unit. You can change the effectiveness of the storage tank and the pump efficiency inside the storage tank, and you will control the inlet temperature going to the parabolic trough collector. This is evaporation pressure, outlet enthalpy. This is for parabolic trough collector. Mass flow rate around 7. Total area, total length, and so on. For bullet heat exchanger, we have to watch the storage medium height levels, some design parameters, molten salt enthalpy, outlet temperature, going to the parabolic trough collector, steam outlet enthalpy, steam outlet temperature, okay, steam pressure, mass flow rate of the molten salt going through to the parabolic trough collector, a number of tubes and exergetic thermoeconomic streams. And this is steam turbine, enthalpy outlet, temperature, drainage fraction, hourly costs, total exergy destruction rate, and so on. It's around from 1 up to it's around 1 megawatts of power with around 1.4 kilogram per second flow rate. For MED, you have to watch steam mass flow rate, feet per effect, in the condenser cooling water, first effect distillate profile, prime profile. This is prime profile. It's from 65 down to 60 because we assigned this one. I'm sure we can change number of effect. You can watch this from previous videos and so on. Okay, don't forget to download our power cycle for this osmosis was especially geothermal power plant. We in this model we connected concentrated solar gas engines, Brighton and Stirling, to drive on pumping power, the geothermal plant. This liberty osmosis, and this is a well design. You are going to discover how many meters you are going to dig in order to generate sufficient power for the turbine unit and so on. Finally, thank you very much for watching. Please like, share, subscribe. Thank you.